Hello everyone, this is Martin Landry again with Planet Earth, and in this short video I want to summarize some points or get back to those points that you were asking about. And one of this is paleomagnetism, or at least there was this kind of image chart in my lecture, and some of you were asking what's the meaning of this, why we have these plus and minus symbols or signs over here. So how do we understand paleomagnetism? Also, I want to speak about the principles, so superposition, horizontality, cross-cutting relationships, unconformity and correlation. So these are the principles that help us think about the relative time. And also we can think about the timetable, the geostratigraphic timetable. We can just call it the geological timetable and try to think about how we can memorize it. So in the first place, to speak a little bit about the paleomagnetism, here what we need to understand is it's all about like the study, the record of the Earth's magnetic field and how it comes together with rocks, because rocks are going to be able often to capture this direction of the magnetic field. So this is the image we first need to think of, and here I have in the first place an igneous rock or a volcanic rock. We can think when it's magma, it's still soft. It just came out of the earth. You can think of a volcano with lava. So it's flowing, the lava is flowing, and there are tiny bits of these materials that contain iron compounds like magnetite. And at that point, when it's still soft, we don't have crystals, we don't have actual minerals. These are pointing in all different directions. So they don't have a magnetic structure, so to say. And when the material solidifies, so the lava or the magma becomes a rock, then these materials like minerals containing or magnetite at all is going to take these directions. So the tiny bits of the molecule basically point in a certain direction. So that's why we have here arrows and why we have here negative and positive symbols. So these are the negative, positive, and all the bits of the rock will be pointing in the same direction at the point of the solidification or crystallization. And then we can just think of how in a global perspective this looks like. We have our planet, we have approximately, we can say usually the northern pole and the southern pole. And so at this point, obviously there will be positive that moves towards the negative pole, but these will be able to swap. So that's the important thing, that we have this magnetic reversal. So reversal of the magnetic poles that happens from time to time. Also the strength of the magnetic field will be changing from time to time, and that's why in this image we can right away think about how this information comes together with plate tectonics. And what we can think of is that we had an ancient continent, say the Pangaea or Laurasia. So over here we have on the left, for example, on the west, New York, over here somewhere. And over here we will have Europe with like Paris in the east. And these were once part of the same continent. They started splitting up. First we have here a rift, and then this turns into an oceanic like ridge. So what we have here is the development of the sea floor, and the sea floor will be made of the magma, basically the material that will come to the surface. And what happens at that point? Exactly what I've been talking about over here. So the magma will crystallize, and whenever this material comes to the surface, at that point, however the planet is behaving, we will have positive and negative orientation or arrangement or direction of these minerals that somehow interact with the magnet, so contain iron in the very first place. And by time we have reversal of the north, the southern magnetic pole. So you can read about this, and also we can say that these are moving, so there's polar wandering happening by time. And whenever we will have this kind of reversal of the magnetic poles, that will be also captured in these rocks. So how they are orientated, and here we're pointing upwards, then the negative will point upward and the positive will point downward. So what can we do then, or why is this important to us, like geologists if we are, is that in the past century they started using like sensors. So the boats or ships were carrying like a sensor, and that was able to sense this magnetic orientation of these rocks. And we could see like a boat was crossing from Paris to New York, is that we have on here the east and on the west the same pattern you see here, that approximately the same lengths of these strips of the oceanic seafloor, so they will be orientated in the similar way, or directing the similar direction in terms of its magnetic charging. And this will tell us or show us how the seafloor was actually spreading. So what we can do now is go to a volcano, and volcanic rocks will also show the actual direction of the northern magnetic pole. We can do the same here. We could go down and grab these rocks from the bottom of the ocean, but actually it's easier just to capture this magnetic direction or orientation of the rocks. And this is how we can in one way prove or at all come up with the idea that seafloor spreading or plate tectonics exists. So this is just to think about how this whole discipline or knowledge about plate tectonics developed with the help of paleomagnetism. That's why we have these negative and positive, like a battery, but we're not speaking here about a battery, we're talking here about the magnetic field of the earth and how it's captured in the actual rocks that developed in time, the past like 200 or 180 million years, if we think of the case of like the Atlantic Ocean, if I was speaking about New York and Paris. So these are located on two sides of the Atlantic Ocean. That's how we can think of seafloor spreading and plate tectonics.